A non-recursively enumerable language. Remember the sort of diagram that I've drawn several times of types of languages, right? There's the regular languages, which are a subset of the context-free languages. And something which is context-free but not regular would be A to then B to then. Then there are the recursive languages. Something which is recursive but not context-free is A to then B to then C to then, right? These are the languages of a total Turing machine. That is a Turing machine which never has an infinite loop for any input. And then we have the RE languages, which is the largest category that we've talked about. And we now have an example of something which is RE but not recursive, and that is the language of the halting problem. The language of the halting problem is something which cannot be computed by any Turing machine with no infinite loops. That's the language of the halting problem. This is the language, remember, of strings which look like M separator X, where M is the encoding of a Turing machine and X is a string which halts when you feed it into M. That is not recursive. You cannot make a Turing machine that accepts this language with no infinite loops. Recursive. What I want to talk about a little bit is a non-recursively enumerable. There are actually even languages which are so weird that they are out here, beyond the recursively enumerable. That means they could not be computed by any Turing machine, whether it has infinite, whether it allows infinite loops or not. All right, this would be things out here. Already things in this category, RE but not recursive, you should view as sort of being impossible for practical real-world computers. This means the fact that it's here but not here means, yeah, you could make a Turing machine that computes it, but sometimes that machine would have to run for an infinite amount of time, and that is not practical. So the universe of like practically computable things would be in here, at least from the point of view where practical means finite time. Of course, finite time often is not practical because that finite time might be very large. But anyway, something in this category you should view as impossible for a real-world computing machine to do. Something out here is like extra impossible. This means even if you allowed the machine to sometimes run for an infinite amount of time, it still couldn't possibly compute anything. That would be something out here. Let's talk about something out there. I am going to give you another weird language. We're not going to be able to express things in easy formulas like this anymore. This is already very weird. The one out here is slightly weirder, although it's not a hard concept. If you recall, LH, this is the language of strings that look like M separator X, where M is a Turing machine which halts on X. All right, and this is recursively enumerable, but it's not recursive. That means sometimes you can do it on a Turing machine, but sometimes the machine might run forever. Another way of saying this is that it is possible to make a Turing machine which will simply verify that M halts on X, but it's not possible to make a machine which will tell you yes or no if M halts on X, because when the answer is no, sometimes that machine would have to run forever, and you would never finally give the answer of no. It would just run forever instead. Anyway, this is RE, but not recursive. It turns out, for similar reasons, I don't want to go into the nitty-gritties of this, but here's a similar language. I'm going to call this LU, because this is what our book calls it. It is this, M separator X, such that M is a Turing machine which accepts X. All right. This, for similar reasons as this, is RE but not recursive. If you want something which has this language, if a Turing machine which is going to tell you whether or not M accepts X, automatically that machine must also be able to tell you if it halts, right? Because accepting is just like a special type of halt. I don't want to get into all the details here, but believe me when I say LU is also recursively enumerable, but not recursive. What that means is, I'll say IE, in terms of decision questions, i.e. a Turing machine can verify that some m accepts x, but it cannot decide yes or no, does it decide x. So if you already know that it does accept, then there is a Turing machine which can make that a verification. That would be the universal Turing machine. That's why it's called LU. This is basically the language associated with universal Turing machines. If you already know that m accepts x, then the universal machine can simulate the m and verify, yes, it does accept x. But if you don't know and you ask whether or not, that actually cannot be done by a Turing machine. So, i.e., a Turing machine can verify that some m accepts x, but cannot decide, yes or no, whether or not m accepts x. All right, this is what it means when I say something is RE but not recursive. It means that. Okay, now I'm going to tell you what is the language which is not even RE. If you're following so far, this is not so hard to. I'll write this as a theorem. LU bar is not RE. This means there is no Turing machine which has this language, even if you allow that machine to have infinite loops. LU bar is not RE. All right, and the proof actually is pretty easy. What if we're going to do by contradiction? So assume, what if LU bar is RE? So we're going to assume LU bar is RE. Then that means that there is a Turing machine. If it's RE, it doesn't mean that you can decide whether or not something is in LU bar, but it does mean if something is in LU bar, you can verify that it is in LU bar. So assume that LU bar is RE, then there exists a Turing machine which can verify that something like m does not accept x. That's because this is the complement, right? LU means m does accept x. It's m hashtag x, where m is a Turing machine which does accept x. LU bar, what I'm talking about now, if it's RE, that means there is a Turing machine which can verify that some m does not accept x. I put the does not because I'm talking about LU bar now. This is the complement of LU. LU is m does accept x, so LU bar would be m does not accept x. All right? So there is a Turing machine which can verify that m does not accept x. Remember also, we already know LU is RE, right? It's actually RE but not recursive, but that doesn't matter so much at the moment. So we know LU is RE, so that means there exists a Turing machine which can verify, this is what I wrote earlier, that some m does accept x. So look at these two things together, right? The first one says that there is a Turing machine which, whenever you give it any m and x, it can verify that m does not accept x. And then there's another Turing machine which can verify that m does accept x. So, given any m and x, we do both Turing machines at the same time. And one or the other will actually halt, right? Because either m accepts x or it doesn't. And whichever one it is, one of these two machines will be able to verify. So given any m and x, we do both Turing machines at the same time, and then one of them will halt, right? Because either x is accepted or rejected by m, and so one or the other of these is actually going to complete its verification. The other might just run forever because these are not total Turing machines. Anyway, we do both Turing machines at the same time. One of them will halt, and so using both machines at the same time, actually, we do have a procedure now for deciding whether or not m accepts x, right? Combining these two machines into one sort of mother machine, this provides an algorithm That is a procedure which you can do using Turing machines for deciding whether or not M accepts X with no chance of infinite loops. Right? Because I'm running those two machines at the same time, one or the other of them will halt, and then I just stop the whole procedure. So this gives me an algorithm for deciding whether or not some Turing machine M accepts some string X with no chance of infinite loops, and that is impossible. This is a contradiction because we already know, I already said earlier that, that this is not possible. This is a contradiction with the fact that this contradicts LU is not recursive, right? What it means to say that LU is not recursive, which I already said, is that there is no Turing machine which can decide whether or not some M accepts X. And I just said we had produced such a Turing machine, such an algorithm. That's not possible, though. So this contradicts the fact that LU is not recursive. All right. All of that to say, LU bar is not RE. So this is a language which you can't do on any Turing machine, even one which is allowed sometimes to run forever. There you go. There are non-recursively enumerable languages. They're very weird, though. I think you would agree with me. One more thing we can say about all this business, about the fact that there are non-recursive languages and even non-RE languages. Remember, no total Turing machine can solve the halting problem. Right? This is what we talked about last time. This actually provides a little resolution to something I kind of left hanging earlier. When we first talked about Turing machines, we discussed the fact that if you add some kind of extra functionality to the Turing machine, it will just result in another equivalent machine. For example, if you allow the Turing machine to have 2 tapes or 3 tapes or how many tapes you want, it doesn't actually make it any more powerful. If you allow the machine to jump while it's moving rather than moving one step at a time, also that doesn't actually make the machine any more powerful. I said at the time, I don't know if you remember, I said anything you can think of that you add into a Turing machine will not change its computational power. Anything you can think of, and I did say at the time, there are actually some very weird things you could do which will change its power, but just you wouldn't think of them. They're not ordinary things that you could explain just in a few words. There are very weird things you can do to extend the powers of a Turing machine, and this actually suggests one of those things. No total Turing machine can solve the halting problem. So, if you wanted to really make the machine more powerful, you could imagine, what if it was a Turing machine, but it also was able to solve the halting problem? Then certainly it would be more powerful than the ordinary Turing machine, because the ordinary Turing machine cannot solve the halting problem. Now, how do you say it's a Turing machine, but it can also solve the halting problem? This is something, of course, this can't exist in the real world. A real world computing machine can't do this. So there's actually no way to describe that in terms of maybe allow the head to do some other kind of motions, because any motion you could think of would be something that in theory you could do in a real computing machine, which is not possible. Anyway, these sorts of machines, so I'm going to say we can improve the Turing machine's power. We can make it more powerful by somehow enabling it to solve the halting problem. This is kind of like, just imagine that the machine could do some kind of magic, whereas in each step, it either, moves to the right or to the left, or it solves the halting problem. And you don't even try to say, how would it do that? Because in the real world, it can't do that. But we can improve the Turing machine by giving it this sort of magical power. And this is referred to as a halting problem oracle. This is the real word that people use when they talk about this. A halting problem oracle. These are sometimes called oracle machines or oracle Turing machines. That is, it is a Turing machine which obeys all the same rules about how the head moves, but it has one extra superpower. It can, whenever it wants to, solve a halting problem. I'm not going to tell you how it does that, because in fact in the real physical world that's impossible. But this is a purely theoretical idea. What if there was a Turing machine which could also solve the halting problem? Is this Turing machine able to do any computation now? Or are there still Turing machines, or are there still types of computations that even such a magical machine could not accomplish? And I'm here to tell you, I don't want to go through the details because this is very abstract and very complicated. But can I just say, a Turing machine with halting oracle, that means it does the ordinary Turing machine stuff, and also at any moment it can magically solve a halting problem. All right, a Turing machine with halting oracle is certainly more powerful than a normal Turing machine. Right? Because the normal Turing machine cannot solve the halting problem. This one can, just by magic. But still, there are languages that it cannot compute. It cannot compute. The Turing machine with halting oracle is not all powerful. Even if you allow the Turing machine to have this halting oracle, you can imagine very weird examples of languages which that Turing machine cannot compute. Here's a question. If I have a Turing machine with a halting oracle, there's some other weird language that that machine cannot compute, if you believe what I said before. Okay then, why don't you give it another oracle for that other weird thing? If a Turing machine with halting oracle, there's still some other problem that it can't solve, all right then, give it that oracle too. Can we just add in more magical powers one by one? In fact, even if you do that, every such machine that you construct will still have languages which it cannot compute. This is a very, I don't know, to me this is philosophically interesting. If you imagine the Turing machine and just keep on giving it like extra magical powers one by one, in fact, those machines, every time you give it more and more magic, there is going to be a few weird languages that that machine still cannot accept. By adding magical powers one by one, it is not sufficient to make a machine that can accept everything. And in that sense, it's kind of there's kind of no such thing as a machine that can accept everything, or such a machine would have to be like purely magical or something. It wouldn't resemble a real world machine at all. Anyway, that's that. Oracle machines. There's a lot that you can say about such things. We are not going to say anything about them.